Hi, I'm Randall Heyman, a university mathematics academic. I'm making quick turnaround videos on YouTube to help lecturers, tutors, high school and primary school teachers, parents, grandparents and students with any mathematical problems and concepts that they have. So if you'd like me to make a video for you or your students, comment below the video and I'll try and help. This is now probably the last video in a number of videos where I've helped a school in California with these three concepts up here, and we've finally got to the end, quotient fields. So in the last video, we talked about integral domains, which are very close to the concept of a field. We just need a little bit more conditionality to get to a field. And quotient fields are really a very natural way to get from integral domains to a field. And the example, the classic example is, well, we've got integers, which the set of integers is an integral domain, and that can go to the rationals, or the set of fractions. And in fact, what I'm showing you, what I will show you, this process takes an integral domain to the smallest field that the integral domain is part of. So let's put up a definition that I've concocted, and then we'll do some examples. So let R, this time it's going to be an integral domain because that's what we're starting with. And I've made the big mistake that I've cautioned people not to do, which is that generally it's better to actually put the operations as well. So let's let that be an integral domain. So here we're just thinking that R is that funny Z, which is the integers. That's the most natural one. Then, so now I'm just going to create another one. How do I create the rationals from the integers? I just use division, and we'll do a similar sort of thing here. So this is the new thing. This will be a field. So I'll do F. I'll say F on G. And what's F and G? Well, F and G are elements of the integral domain. We'll require that G doesn't equal 0. So that's the set. And it will have the same addition and multiplication as we had in the integral domain. So I better put the proper bracket at the end here. Oops, let me just write this a little bit better. Multiplication, and then that. Then this set is a field. Is well, we can call it the quotient field. And I hope it's obvious from that it is actually a field. Good. So that's great. Let's do some examples. Before we do, I'll just make a quick mention of something that you'll see if you get into this in a bit more detail. And if you look at the integers, the rationals, fractions, we know that 3 on 2 is the same as 6 on 4. So up here, it's almost like if I was just going to do this set, I would have 3 and 2 and 6 on 4 would be different elements of the set. But what we do is we use the concept of what we call equivalence classes to remove that problem. So we define an equivalence class using the rule that, you know, all equivalent fractions are equivalent. So I just mentioned that in passing, and you can follow up on that if you want to explore that a bit further. So let's do some examples. So the first example is the integers become the rationals, which we've discussed a bit. The second one is, let's talk about what are called the Gaussian integers. So this is now the set of, we take any integer and add any integer times I, where I is the square root of -1. So this is a complex example. and we'll use the normal addition and multiplication that we use for complex numbers. And well, that can become so we'll call this, I don't know, I'll call this funny G. I'm not sure. Funny G. And so this can become, the quotient field would be the set of F on G, such that F and G are now elements of this funny G set. G is not equal to 0. Plus and times. So here we might be thinking of, you know, 1 plus 2i on 3 plus 4i. That's a very natural way to go from these Gaussian integers to this field of fractions. And then the final one, which is relevant to what we were discussing, just move this across to hide that field stuff that we had before. So this is very relevant, this one, because we discussed it quite a bit in some of the previous videos, and that's, let's go from ZX. Remember, this was the ring of polynomials, and it's actually a integral domain as well, as it turns out. So I'll so this is the set A0. There's just polynomials. So the set of all polynomials, where m, I suppose, needs to be a positive integer or 0, positive integer or 0. So that's a big set there. Actually, we need a little bit more detail, don't we? We better put what the AIs are. So we'll let the AIs, of course, be integers. So that's the set, and we just use normal positive and multiplication that we use when we're doing polynomials. Good. So what does that turn out to be? Well, that just turns into be, it's actually QZ, which is equal to the set of F on G. And this time I can actually name F and G are actually in QX. G better not be equal to 0 plus times. So this is a quotient field, QX. And here, you know, I'm thinking here, example, 2x plus 1 on 3x plus 2. And in particular, this has a multiplicative inverse, because we know that if we multiply it by this, we get 1. So that's quotient fields. So, okay, let's just finish up with that. So this was originally asked of me by Ping Q, and I think that's how he pronounces his first name, in California, who asked me to go through these 3 things. Sorry, you can't see them properly there. Let's move that across a bit. There we go. There we go. And I finally done it. So I suppose what I can do is I could actually rub all these out and put tick, 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 all done. So if you've got any questions on any of this, please comment below. Any questions on anything in mathematics, also comment below in the video. And to that teacher in California, by all means, send me a comment, let me know how you get on going forward. Thanks very much.